Stamping dies are the tools that shape and cut sheet metal parts. The design and production of dies is a specialized profession in which prepared drawings are translated into stamping dies by skilled craftsmen, known as die makers. These stamping dies are then mounted in presses, where sheet metal is fed to them either individually as cut blanks or continuously from coils. There, the press provides the force to close the dies where they form the sheet metal into finished parts. To better understand how stamping press dies operate, it is necessary to understand the sheet metal properties needed to produce acceptable finished parts. The main manufacturing requirement for most sheet metal applications is good formability. This is the sheet metal's ability to deform into intricate shapes without defects in the finished part. In all sheet metal forming operations, one or more types of deformation are involved, including bending, stretching, and/or drawing. Part shape largely determines the relative severity of the sheet metal's formability, especially where drawing and stretching occur. But other factors also influence formability. Those include the ductility of the metal, the die design, the stamping press, press speed, lubrication, the sheet metal feeding mechanisms, and monitoring systems and controls which safeguard and synchronize the operation. Because of these various factors, formability differs from one part or operation to the next. Forming a part with force that exceeds the metal's ability to resist tearing can result in failure. Failure during forming can also occur due to impurities or voids in the metal. Sheet metal thickness for stamping varies widely, from foils as thin as 1/1000th of an inch to metal up to 1 inch thick. Most stampings, however, are made from metal ranging from 20 thousandths to 80 thousandths of an inch thick. Ferrous and non-ferrous metals differ in their ability to deform, as well as in tool design and stamping procedures. The most common ferrous sheet metal type used in stamping is low-carbon or mild sheet steel. It is used mostly in the automotive industry and has good formability characteristics. Aluminum and its alloys are among the most commonly fabricated non-ferrous metals and are available in various strengths and formability combinations. Other non-ferrous metals that can be formed include copper and its alloys of brass, beryllium copper, phosphor bronze, cupronickel, and nickel silver. The term die can be confusing since it represents two different things. As a generic term, it represents the entire press tooling used to cut and form metal. However, the term die can also refer to only the female half of the tool set. The male punch mates with the female die, and working in opposition to each other, they form shapes and punch holes in sheet metal. The term die set refers to the upper and lower die assemblies, which are also called punch and die holders or shoes, as well as other components. Die sets can take many forms, shapes, and sizes. The upper half of the die set is clamped to the press ram, while the lower half is secured to the bolster plate on the press bed. The die halves are opened and closed by movement of the press ram. Guide pins sliding in matched bushings or ball bearing bushings align the upper and lower half of the die set. Cutting, which includes shearing, blanking, hole punching, and trimming, is the most common press-working operation using dies. Shearing is a process by which large sheets of material are cut into smaller sections. These pieces are generally used in later operations. Blanking is a form of shearing that cuts sheet metal stock around the complete perimeter of a shape to form a workpiece blank. Reference to a blank in stamping usually implies the need to perform subsequent operations to the workpiece. Punching is the cutting of a slug from the sheet metal stock to produce a hole. Hole punching, as well as other forms of die cutting, requires specific clearance between the punch and the die. Proper clearance is a function of the type, thickness, and temper of the workpiece material. During punching, the stock is stressed between the cutting edges of the punch and the die. As the punch penetrates the material, stresses build up until fracture occurs. Close inspection of a die-cut edge of sheet metal stock reveals a burnished edge where the punch penetrated the stock, followed by a rough edge where fracture occurred. Mild steel generally separates when approximately 1/3 of the stock thickness has been penetrated. However, when harder materials are die-cut, penetration by the punch may be less than 1/3 the material thickness, and softer materials may require almost full punch penetration before fracture occurs. After a part has been formed, a trimming die is utilized to remove the excess scrap metal from the workpiece. Forming is a broad term for metalworking processes in which the shape of a punch and die is reproduced directly in the metal. Some common forming operations done with press-mounted dies include drawing, bending, flanging, and hemming. Drawing shapes a flat pre-cut metal blank by forcing it into a die cavity with a punch without excessive wrinkling, thinning, or fracturing of the metal. Various complex forms may be produced by drawing. Drawn parts may vary in size from small parts up to aircraft and automotive parts large enough to require mechanical handling equipment. For properly draw-formed parts, the force exerted by the punch must be great enough to draw the metal over the edge of the die opening and into the die. Additionally, the drawn metal must have a combination of strength and ductility to avoid rupture in the critical area where the metal conforms from the punch face to the punch sides. Compressive forces on the metal in the area beyond the die's edge will cause the metal to buckle. If this metal were pulled into the die, buckling would increase until the metal ruptured. To prevent buckling, the blank must be held tightly by a blank holder. On most forming presses, the blank holder is an outer ring through which the inner ram or punch passes. The blank holder holds the workpiece against the draw die to control metal flow as the punch forms the shape. In practice, the blank holder must exert less pressure against the blank than the punch, so metal can flow into the die, yet it must exert enough pressure to prevent wrinkling. Factors determining necessary blank holder pressure vary from part to part, but include the severity of the draw reduction, metal properties and thickness, die lubrication, and other factors. Bending is performed on sheet metal to gain rigidity and to produce a part of desired shape. Bending is usually done to make structural stampings, such as brackets, braces, and supports. Flanging is a forming operation similar to bending, except that the flanged edge is shorter and narrower compared to the overall part size. A flange can be bent down along a straight or curved line and is used for appearance, rigidity, edge strengthening, removing a sheared edge, and to provide an accurately positioned fastening surface. In sheet metal forming, hemming is utilized primarily to provide a smooth, rounded finished edge and to attach sheet metal parts together. There are 4 basic types of hems. Those include the flat hem, which can be used with materials having high ductility, the teardrop hem, which is used on materials lacking the ductility required to form the flattened hem without cracking, the open hem, and the rope hem, which are used to join sheet metal parts together. Multiple operations may be carried out on sheet metal stock either at a single die station or at multiple stations within a single stroke of the press. Dies used in single station operations can be either compound dies or combination dies. Compound dies are press tools in which only cutting operations are done, usually blanking and hole punching. Combination dies are press tools in which a cutting operation, usually blanking, is combined with shaping or forming operations. Multiple station operations are done with dies that have several stations. Each station simultaneously performs a single step in a series of operations needed to complete a part. Finished workpieces are discharged with each stroke. Multiple station operations can be performed using either progressive dies or transfer dies. In progressive die operations, parts are made from continuous coil stock and remain connected to the stock by a carrier strip during each successive operation until the final cutoff and discharge from the die. In transfer die operations, parts are blanked before or at the beginning of the sequential operations. Mechanical transfer devices grip and move the individual workpieces from die station to die station within a single die to complete a progression of operations. With large workpieces, a tandem press line may be utilized. Parts are transferred by gripping devices from press to press, instead of within a single die. Each press within the tandem line holds its own tooling and performs specific operations to form, trim, and pierce the part. Friction is inherent in die cutting and forming processes. Forces applied to cutting and forming tools are transferred to the sheet metal by direct contact. For this reason, lubrication is vital for successful sheet metal forming. A lubricant's main function is to minimize surface contact between the tooling and the workpiece. As a result, workpiece surface quality is directly related to the properties and behavior of lubricants. Effective lubrication results in controlled friction, reduced force, power requirements, and tooling stresses. Proper lubrication also extends tooling life and improves product quality by eliminating surface damage. Choosing the proper lubricant requires careful consideration regarding the type of operations being performed, tooling design and materials, the metal to be formed, press speed, and lubricant application method. Lubricants for stamping range from light mineral oils to heavy drawing compounds. These lubricants can be oil-based, water-soluble, or synthetic. The objective in applying these lubricants is to apply the correct type where needed, at the right time, and in the proper amount. The 5 primary methods used for applying die lubricants include manual, drip, roller, spraying, and flooding. The most basic lubricant application is done by hand with a roller, brush, swab, or sponge. Manual methods do not require expensive equipment, but can be uneconomical because of wasted lubricant, poor uniformity, and excessive labor costs. Drip application simply allows the lubricant to drip continuously on the stock strip. It can be used for small parts being blanked or formed with light-bodied, easy-flowing lubricants. Roller coating of lubrication is widely used. There are 3 types of roller coaters: unpowered, plain, which is unpowered with a recirculating system, and powered. The preferred position for a roller coater is between the stock feeding equipment and the press. Spraying systems for applying lubricant include air spray, airless spraying, and electrostatic. The flood lubrication system continuously recirculates and filters a lubricant, allowing a heavy flow volume to be used when necessary without waste. Die making is as much an art as it is a science and requires a great deal of experience and expertise to construct a die that will manufacture an acceptable part. Factors such as metal flow, friction at the tool workpiece interface, and the behavior properties of the stamped material make it difficult to predict the final shape that a die will produce. One analytical tool used by die makers to help assure sheet metal part design formability is called Circle Grid Analysis, or CGA. This technique permits measuring the type and severity of deformation that occurs at various points on a stamped part. First, a grid consisting of a pattern of small circles is etched on the surface of the blank prior to forming. This grid deforms with the blank allowing point-to-point calculations of the deformation that occurred during the stamping operation. Analyzing the stamped grid pattern suggests the location and type of rework that must be performed on the dies to produce easily manufactured parts. Once changes are made, the circle grid analysis process begins again. By observing the resulting changes in metal deformation, the tool room technicians can identify the corrections needed for following tryouts. This process continues until an acceptable part is made. Computer software programs are also available that can assure that proposed stamping designs can be manufactured with certainty, with the objective of minimizing the lengthy fine-tuning process of die making. In metal forming operations, the part is shaped by tooling impacting on the metal stock, often achieving the final shape with little or no scrap. Sheet metal stamping transforms metal into functional products by applying the force of a moving ram to tooling located within the stamping press. Stamping's primary advantage is the ability to transform two-dimensional sheet metal stock into three-dimensional finished components at a relatively high rate of speed with minimum operator intervention. Sheet metal stampings range from simple stamped parts to complex curved shapes. Common examples of stamped sheet metal parts are found in automobile manufacturing. The stamping press transforms steel into numerous frame and body components. Various products in other industries are also fabricated largely from stamped sheet metal components. It is essential to understand that the stamping press simply provides the force for the stamping operation. The finished stamping is determined by tooling within the die, which is located within the press. Presses use either mechanical or hydraulic power to force the tooling together and form the part. Mechanical sheet metal stamping presses vary widely in size. Benchtop presses are among the smallest and are rated as low as 5 tons capacity. Extremely large multiple or tandem press lines rated in thousands of tons are used for stamping very large, complicated workpieces. Press stroke speeds can vary from 8 or 10 strokes per minute to operating speeds of up to 1,800 strokes per minute. Both mechanical and hydraulic presses are commonly classified by the design of the frame that supports the moving elements of the press. The two predominant press configurations are the gap frame, sometimes called the C-frame, and the straight side press. The principal feature of the gap frame configuration is its C-shaped throat opening. Advantages of the gap frame press are ease of access to 3 sides of the die area, as well as the need for less floor space than the straight side press. In press force capacities ranging from 35 to 60 tons, gap frame presses may cost approximately half as much as straight side presses. The main disadvantage of the gap frame press is an unavoidable angular misalignment that occurs during stamping operations. This deflection of the C-frame can only be limited by very robust frame construction, which adds to the weight and cost of the machine. In many applications, however, this misalignment is not a problem. The frame of the open back inclinable or OBI style of gap frame press pivots at the base. This feature aids in finished part or scrap discharge. Generally, however, the open back stationary or OBS style of gap frame press is used more often, with parts removed from the die by timed blasts of air, automatic unloading devices, or conveyors. Straight side presses derive their name from the vertical columns or uprights located on either side of the machine. The housing or frame of most straight side presses is held together in compression by pre-stressed tie rods, although some straight side presses have solid frames. Angular deflection during stamping is not an issue with straight side presses. For that reason, dimensional accuracy of stamped parts and the need for die maintenance often improve with the selection of a straight side press. The main structural components of a straight side press include the crown, the columns, bed, and bolster. The crown serves many functions, depending upon the design of the machine. Typically, the motor, flywheel, clutch, and brake mount on the crown. The crankshaft end bearings may also be located in the crown or, in some cases, in the columns. The columns support the crown and have attached adjustable guides called gibs that guide the slide. The gibs ensure proper parallelism, squareness, and sliding fit between press components. The bed is the base of the machine. It must rest on a solid, level foundation to ensure proper machine functioning. The bolster adds stiffness to the press bed and assists in spreading the load evenly over the bed's structural members. The bolster has T-slots, or tapped holes, to permit secure fastening of the die. In a mechanical press, an electric motor supplies the energy needed to stamp parts. There are a number of moving parts that store, control, and transmit that energy to the die and workpiece. These parts include the flywheel, gears, clutch, crankshaft, pitman, connection, slide or ram, counterbalance, and brake. The flywheel stores the energy supplied by the motor. The gears reduce the speed and increase the torque delivered by the flywheel through the clutch. This is known as gear reduction. The clutch controls the coupling and transmission of the flywheel's energy to the crankshaft, or eccentric drive on eccentric style presses. The pitman transmits the motion of the crankshaft to the slide by means of a bearing known as the connection. On eccentric presses, the eccentric strap transmits the motion. The slide, or ram, is what the upper die is fastened to. The counterbalance offsets the weight of the slide, upper die, and attached linkage during press operation. The brake stops the press and holds the slide and attached mechanisms in place. Various press parts, such as the pitman, connection, and bolster, have similar functions in both straight side and gap frame presses. Several drive arrangements are used on mechanical presses to transform the rotary motion of the drive motor through the crankshaft to the reciprocating motion of the slide. These arrangements include direct drive, single gear reduction, and double gear reduction presses. In non-geared or direct drive presses, the flywheel is mounted to the end of the crankshaft and driven by belts from the motor. Higher operating speeds are possible with this arrangement than with geared type drives. Other advantages of this simple design include fewer moving parts to wear out and less frictional loss of mechanical energy. Certain factors limit application of the direct drive, however. The full rated force of the machine is only available very close to the bottom of the stroke, and the ability to deliver rated forces is substantially reduced if the press operates at less than full speed. In single gear reduction presses, the flywheel is mounted on the back shaft and power is transmitted through a pinion to a main gear mounted on the crankshaft. A problem occurs with single end drive presses, however. Angular misalignment, proportional to the torque transmitted through a crankshaft with two throws, causes the side of the ram nearest the driven end of the crankshaft to reach bottom dead center before the other side. This results in a ram tipping alignment error. Angular misalignment of the crankshaft is avoided when the crankshaft is driven equally on both ends. This provides more accurate alignment under load than with single-end drive systems. Additionally, this angular misalignment is not an issue on eccentric gear presses, in which an eccentric is fastened to the main gears, thereby eliminating the use of a crankshaft altogether. Double gear reduction presses have two gear reductions from the flywheel to the crankshaft. These machines normally achieve a speed range from 8 to 20 strokes per minute and are used for difficult applications such as heavy deep drawing, cold forging, and flanging of large parts. Clutches and brakes are vital elements of a press. Virtually all mechanical presses transmit the energy stored in the flywheel to the slide by means of a clutch mechanism. Otherwise, the slide would cycle continuously whenever power was applied to the flywheel. When the clutch is not engaged, the slide is stopped and maintained in a stationary position by a brake. Many older presses use a mechanical full revolution clutch, which when activated cannot be disengaged until the crankshaft makes one complete revolution. Most modern presses are equipped with an air friction clutch and brake arrangement, commonly called a partial revolution clutch, which can be disengaged at any point in the stroke before the crankshaft has completed a full revolution. The air friction clutch permits rapid, dependable stopping and engagement in mid-stroke. The force capacity of a mechanical press is the maximum force that can be exerted at a specified distance above the bottom of the stroke by the dies against a workpiece. It is expressed in tons or kilonewtons and is often the major consideration in the selection of a press. Other criteria that determine force capacity of a press are flywheel energy and torque capacity. The flywheel receives and stores energy from the motor until a certain amount is removed by each working stroke of the press. Once the flywheel is up to speed and the press is not being cycled, the motor need only supply enough energy to make up for frictional losses until the next stroke. Torque capacity is the ability to transmit the energy of the flywheel through the gears, clutch, crankshaft, connection, and slide into the die without exceeding the safe working capacity of any component. Geared presses allow the flywheel to be rotated faster while the slide speed is reduced. Gearing does not increase force or energy capacity. The gear ratio is primarily a means for obtaining an efficient flywheel speed. The definition of high-speed mechanical press operation in terms of strokes per minute is not universally agreed upon. As a general rule, high-speed operation involves press speeds of 300 strokes per minute or greater. The press speed for small high-volume parts can exceed 2,000 strokes per minute. However, such presses generally operate at 1,000 to 1,400 strokes per minute for improved die life and performance, more consistent workpiece quality, and easier material handling. Machine size and part configurations are factors affecting press speeds, as are inertia and vibration of moving parts of the press. Common factors in presses designed for high-speed operation include compact, robust construction, with special attention given to close fit and lubrication of bearing surfaces. Excellent alignment of both the press and the die is critical, with the press and die considered as a single system. Hydraulic presses are the alternative to mechanically driven presses. These presses use one or more cylinders and pressurized fluid to provide the required motion and force to form or blank workpieces. While mechanical presses are still the predominant type, hydraulic presses are becoming increasingly more popular. There are metal stamping applications where hydraulic presses offer certain advantages, and in some cases are the only machines that can be used. One of the major benefits is that the full force of the hydraulic press can be delivered at any point in the stroke, not just at the bottom of the stroke as with a mechanical press. Deep drawing and forming applications often require large forces very high in the stroke. Few mechanical presses have tonnage capability to permit such applications. The stroke of a hydraulic press can also be adjusted to provide optimal part clearance before cycling again. Moreover, because the desired preset hydraulic pressure provides a fixed working force, it is well suited for different tool heights and various material thicknesses. Hydraulic presses are more compact than mechanical presses of comparable capacity and have fewer moving parts and are ideally suited for many applications, such as non-automated operations and small lot sizes. Proper selection of a press is essential for successful and economical operation. It is important to note, however, that no general-purpose press exists that can provide maximum productivity for all applications. Compromises must be made if a press is to be used for more than one job. Factors that must be considered during press selection include size, force, energy, and speed requirements. The press must be capable of exerting force in the amount, location, and direction, as well as for the length of time needed to perform the specified operations. Other press selection considerations must include the size and geometry of the workpieces, operations to be performed, number of workpieces to be made, production rate needed, workpiece accuracy, finish requirements, and equipment costs. Press controls involve electrical, electromechanical, pneumatic, hydraulic, electronic, and other equipment used to control the operation of presses. Complexity of controls ranges from a simple starter and disconnect switch to a sophisticated multi-motor, multi-function control incorporating a variety of sensors, control systems, and devices. In addition to controlling the motion of a press's moving elements, a control system should allow a stamping operation to yield consistent, predictably high production rates without jeopardizing the safety of operating personnel, the press, or dies. Systems for controlling mechanical power presses are mostly electromechanical or solid state. However, computer numerical control or CNC systems and programmable logic controllers or PLCs are also being used, especially on more complex, highly automated systems. Self-checking and diagnostic features with fast response to sensors are becoming increasingly important in automated stamping operations. No matter what type of press is used, sheet metal stamping cannot begin until stock is fed into the die. A wide variety of equipment is available to transfer sheet metal material to, from, or between presses. The feeding of blanks or previously formed stampings to presses is accomplished in several ways. One of the most common is manual feeding, which is generally limited to low-volume production. Manual feeding requires the use of point-of-operation guarding or hand-feeding tools to keep operators' hands and fingers out of the die area. Magazines holding stacks of blanks can be fed automatically one at a time by vacuum cups and moved to the die by transfer units. Robots are also used for press loading and unloading. Sheet metal stock is often used in coil form. Coils are available in various widths and a range of thicknesses. Coil stock is fed incrementally between the die halves within the press by a stock feeder that operates automatically in synchronization with the press cycle. Two major types of press feeds for coil stock are slide or gripper feed and roll feed. Both of these feed types can be further subdivided into press-driven or independently driven types. Air slide feeds are powered by an air cylinder. Like mechanical slide feeds, most have grippers or clamps that reciprocate on slides between adjustable positive stops. Roll feeds advance stock by pressure exerted between intermittently driven opposed rolls, which allow the stock to dwell during the working part of the press stroke. Independently driven roll feeds are driven by self-contained power sources and provide the most practical method of feeding material in long lengths. Using coil stock to feed material to a stamping press offers benefits such as reduced material costs and increased operating efficiency. Use of coil stock, however, requires investment in coil feeding equipment. Coil lines can vary in cost and complexity, depending upon the application. The basic components of most coil lines include the uncoiler reel, which can be either powered or non-powered, a stock straightener and leveler, a stock feeder, which advances the material into the stamping press, and a scrap chopper. Uncoiler reels hold the coil stock on its inside diameter by mandrels and can handle reels from 1/4 inch wide weighing a few hundred pounds, to up to 96 inches wide, weighing up to 100,000 pounds. Sheet metal stock, as it is uncoiled, has a set or curvature, which the straightener or leveler removes by flexing the material between opposing adjustable rollers as it moves towards the press, thus providing flat material for feeding into the stamping die. If the scrap is not cut into recyclable pieces by the stamping die, an external shear called a scrap cutter is used to cut up the remaining skeleton.